Hello everybody. We are going to get started with our 10.2 lesson on liquids and gases now. So we're starting off with phase diagrams. On the very top you'll see two different phase diagrams, one for H2O, which is water, CO2 is over here on the right. Now immediately you'll notice a couple of differences in these graphs, the main one being that this slope is negative for water and the slope is positive for CO2. And we're going to explore the reasons for that. But first let's label some important points. So right here, in the very, very center, this dot, this is called the triple point. So triple, we're obviously referring to 3, so this is the point where all three phases coexist at the same time. So solid, liquid, and gas are all in equilibrium. Here, this point is the critical point. The critical point is the temperature and the pressure above which H2O cannot exist anymore as a liquid or a gas. It's considered a supercritical fluid or a plasma after this point. So you can draw lines like this and write SCF for supercritical fluid. Same thing over here. You have your triple point and your critical point. So one thing I would like to talk about is the difference between those two slopes. So if we notice here with water, if we hold our temperature constant, say we just pick any temperature right here, we're going to hold that constant, and the only thing we're changing is the pressure. So we're going to go from a higher pressure to a lower pressure. Notice that in water, we go from a liquid to a solid when we decrease our pressure. And for CO2, if you're decreasing pressure, so you start at high pressure in a solid, again holding your temperature constant, and you're decreasing that pressure, you're moving from a solid to a liquid. Now, if we think about this, this all has to do with intermolecular forces. So H2O has strong hydrogen bonding. And the way that the H2O molecules orient themselves, it leaves holes in the structure. So solid H2O is much less dense than liquid water. And that makes sense. We can see that if we put ice cubes into a cup of water and we see that the solid floats. So if we release some of the pressure, we decrease the pressure, we're going from a liquid to a solid. And that's pretty rare, and that's due to the fact that H2O has these very strong hydrogen bonding capabilities. Most other things are like CO2 in that they go from a solid to a liquid. If you are decreasing pressure or if you're increasing pressure, you're going to go from a liquid to a solid. Okay, that aside, let's go ahead and move on. So example 1, we are mostly going to concern ourselves with the phase diagram for water for the purposes of our examples. So number 1, identify the normal melting point, normal boiling point for H2O. Anytime you see this word normal, so normal will refer to 1 atmosphere. So whenever you see normal in front of melting point or boiling point, say if they're going to ask you what the normal melting point is, what is the temperature of the melting point at 1 atmosphere? And you would read that here. Oh, 100 degrees. So the normal melting point, MP, I'm just abbreviating for melting point, is the temperature at 1 atmosphere at which the solid and liquid states are at equilibrium. So they're exactly the same. So the point at which your solid starts to turn into a liquid. And when it starts to turn into a liquid, you really have some molecules of solid still and some molecules of liquid, so we say they're in equilibrium. So let's start temperature. And if we were going to write a chemical equation for this, we would say that if we added heat plus H2O in the solid phase, ice, so if we heat up ice, obviously we're going to get liquid water. And I'm using again my double arrow because we are in equilibrium at our normal melting point. So H2O liquid. Alright, what is the normal boiling point? Same thing, except for now it has to do with a boiling point. So normal again, referring to that 1 atmosphere. And boiling is when we're going from a liquid to a gas. So this is the temperature. At 1 atmosphere. At which the liquid and gas states are in equilibrium. And similarly, as we did before, heat plus H2O liquid. You heat up some liquid, and you can think about this as like boiling water on the stove. You have liquid water, and you see all this water vapor coming off, which is H2O gas. And that's because we added energy. Alright, next, describe what happens when a sample of water, solid water, is heated from negative 10 degrees Celsius to 200 degrees Celsius at 1 atmosphere. So I drew a diagram, a heating curve, to kind of explain this. So if we look at the y-axis, this is our increasing temperature. And I'm starting from negative 10 Celsius arbitrarily because that's what the question's asking us to do. And then along the x-axis, this is the amount of energy that the system now holds. So, say we're starting here at negative 10 degrees Celsius. We have some solid down here. This is H2O. And it is solid at negative 10. So, when you put energy in to the system, and you're moving over to the right here, the temperature of the ice is going to increase. But it's not going to melt right away. So let me say that again. You're putting energy in, you're increasing the temperature. The ice is going to absorb that, and so we're going to have heating. So the solid's going to be warming. So the solid is warming here. And the solid's going to continue to warm until it hits this particular point. And this particular point is the freezing point. So at the freezing point, 0 degrees Celsius, the molecules have absorbed enough energy to be moving fast enough to be able to break the intermolecular forces between them. So when you break those intermolecular forces that are holding your solid together, you now begin to form a liquid. So here, after your solid warms and it hits your melting point, you're going to move along, and this is going to melt to a liquid, so we call this melting. Now, remember, in melting, you actually have both phases coexisting at the same time. So you have some parts of the substance that are solid and some other parts of the substance that are liquid when you're getting to this point. So this is starting to melt. All the energy going in is just breaking those intermolecular forces, and notice the temperature remains exactly the same. Temperature is not going up. And then, after you have enough energy, and everything is broken, at the end of this curve, you're just going to have a bunch of liquid, no more solid. Then, when you have a bunch of liquid, you're going to warm up your liquid. So this is liquid warming. Until it hits its boiling point. And for water, that's 100 degrees Celsius. And again, the same thing happens. When you get to this point, you've put enough energy in, the molecules are moving fast enough that they can break the intermolecular forces holding the liquid molecules together. So now you start forming a gas. So this is forming a gas, or vaporizing. Then you can go ahead and continue to add energy past this point for a long time, and you're going to get your gas warming. This is one of the reasons that if you've ever gotten a steam burn, it can be much worse than getting boiling water on you, because steam is much hotter. And I mean, this can go really high, absorb a ton of energy, and still stay in the gas phase until it gets to past that critical point that you can really burn yourself quite badly. So that's a heating curve. I suggest that you sketch this out for yourself on another sheet of paper and maybe just stick it with your notes. Okay, moving on. So we're going to go ahead and explain how that happened in words. So describe what happens when that sample of H2O is heated from negative 10 to 0 degrees Celsius. So I'm just going to paraphrase what we just wrote on the other side. So first, the solid warms. From negative 10 to 0. At which point it melts into a liquid. Then the liquid increases in temperature until 100 degrees Celsius when the liquid boils, forming a gas. Then the vapor that we have after that point is going to continue to increase in temperature, and here we're stopping our heating at 200 Celsius. So it's going to increase in temperature until it hits 200 degrees Celsius. All right, we can look at that also on our phase diagram. So if we're at 1 atmosphere here, and say this is, I don't know, here's our temperatures, so some point over here it's not labeled as -10. So your solid is going to warm up from -10 until it hits about 0 degrees Celsius, right around here, at which point it melts into a liquid. So on this line right here, whenever you run into this line, that's the melting point, because you're going from solid to liquid here, so that's the point where the solid and liquid phases are in equilibrium. So you're going to keep moving, and that liquid's going to keep increasing in temperature, keep heating up, until you hit the boiling point. And here, that's 100 degrees Celsius in water at 1 atmosphere. The normal boiling point is 100 degrees. So at this point, again, you're in equilibrium between the liquid and the gas phase. And then you're going to increase your temperature until 200 degrees in this case. So your gas is going to end up at 200 degrees Celsius. You're not going to form anything past that. Okay, now describe what happens when a sample of H2O is heated from -10 to 200 at 0.001 atmospheres. So now say we look at 0.001 atmospheres. It's going to be much lower. So way down here. So here is our 0.006. That's our triple point. 0.001 is going to be below that. So if we're below that line, I'm just going to use a different color. So if we're below that line, we can see that we're not going to run into the liquid phase at all. We're going to go straight from solid to gas. We're going to sublime at a lower pressure. Now, sublimation goes directly from solid to gas. So the solid warms up. From -10 to its sublimation point. And then it sublimes to a gas. Then the vapor warms up until 200 degrees Celsius. All right. Lastly, define triple and critical point. Well, we already talked about what those are. The triple point is the point at which the solid, liquid, and gas states all coexist in equilibrium, and is a temperature and a pressure. So here's the triple point for water, and here's the triple point for carbon dioxide. So just writing that down, the triple point. That is the point at which solid, liquid, and gas states all exist in equilibrium. And again, this is a temperature and a pressure. The critical point, that's that point up here, is the point above which, so the temperature here and the pressure, above which in this whole area, H2O can only exist as supercritical fluid, also known as a plasma. No, actually, sorry, this should say point above which. The substance as a supercritical fluid. Also known as a plasma. And again, that is a pressure and a temperature. Okay, that's it for the first section on phase diagrams. Please see the next video for page 2, which is all about properties of liquids.